Lake Kivu, the most dangerous lake you've never heard of. Picture a lake, big, beautiful, calm. Wooden fishing boats with sun-bleached sails drifting across the surface. Green hills rising from the shoreline, dotted with cities, markets, schools, hospitals. 2 million people living within sight of this water. They drink from it, cook with it, fish in it, move cargo across it. Kids swim near the banks. The sunsets are soft and golden, the kind that end up as desktop wallpapers. Nothing about this picture signals danger. Nothing about it says, pay attention. Now picture what's underneath it. Starting at about 800 feet below the surface and extending to the bottom at nearly 1,600 feet, 300 cubic kilometers of dissolved carbon dioxide and 60 cubic kilometers of dissolved methane. That is not a typo. 300 cubic kilometers of CO2, roughly equivalent to 2.5 gigatons, about 5% of global annual greenhouse gas emissions, sitting in solution, invisible, pressurized, held in place by physics. If that gas were released at once, it would fill the surrounding valley with a dense, invisible, suffocating cloud extending for miles in every direction. The lake is called Kivu. It sits on the border between Rwanda and the Democratic Republic of Congo, and it is one of the most quietly alarming natural systems on Earth. Not because it looks dangerous, precisely because it doesn't. To understand what makes Kivu different from any other large African lake, you need one concept: stratification. Most deep lakes work like a slow conveyor belt. Cold water at the surface is denser than warm water below, so it sinks. Warmer water rises, and the layers mix, seasonally, gradually. Gases that accumulate in the depths get carried upward and released harmlessly into the atmosphere. The system breathes. Nothing builds up. Think of it as a window that opens regularly to let out the stale air. Kivu's window has been nailed shut. The deep water in Kivu receives a constant input from underground springs loaded with dissolved salts. Salt water is significantly denser than fresh water. It sinks and stays sunk, forming a stable layer that doesn't rise and doesn't mix with the water above. Between layers, there are sharp chemical boundaries, chemoclines, that hold like walls. Scientists describe the temperature and chemical profile of Kivu as a staircase, step-by-step structure, with each layer distinct from its neighbor in salinity, temperature, density, and gas content. These boundaries have held for decades, centuries, possibly millennia. Here's the part that flips the intuition. In Kivu, the deep water is warmer than the surface. That's backwards. In most lakes, cold equals deep, which drives the mixing cycle. In Kivu, volcanic hydrothermal vents heat the bottom water, but the high salinity keeps it anchored down despite the warmth. The system is thermally inverted, warm below, cold above, held in place purely by the density difference. And the whole time, invisible processes run continuously in those deep layers. Volcanic sources pump CO2 into the deep water. Magmatic carbon dioxide rises through the Earth's crust, passes through hydrothermal vents, and dissolves under the immense pressure of nearly half a mile of water above it. Simultaneously, microorganisms, archaea living in the oxygen-free deep, process organic material and volcanic hydrogen and produce methane. Both gases stay dissolved under that pressure, the same way carbonation stays dissolved in a sealed soda bottle. As long as the pressure holds, the water looks completely normal. No bubbles, no smell, no sound. Even the fish don't know they're swimming above a massive gas reservoir. There's a third gas worth naming: hydrogen sulfide. It's also present in Kivu's deep water, toxic at far lower concentrations than CO2. In a large-scale release, it would add a poisonous component to an already suffocating cloud. 3 gases, 1 reservoir, and a lid made of saltwater chemistry, stable as long as nothing disrupts the balance. The phenomenon that keeps geologists up at night is called a limnic eruption, or, more plainly, an explosive lake degassing event. The mechanism is straightforward. And that simplicity is exactly what makes it so dangerous. Take a carbonated soda bottle. Cap sealed, pressure intact. The water is clear, no bubbles, nothing moving. Open the cap. Pressure drops, CO2 comes out of solution, bubbles race to the surface. Now imagine the bottle is a lake almost 1,600 feet deep. And instead of unscrewing the cap, someone shakes the bottle. A seismic tremor, an underwater landslide, a volcanic event. If deep water supersaturated with gas begins rising for any reason, the pressure on it drops. Gas starts coming out of solution. Bubbles make the water lighter. The water rises faster. Pressure drops further. More gas comes out. The process accelerates itself. This is a positive feedback loop. Once it starts, it runs until the available gas is exhausted. The eruption could last minutes or hours and pull millions of cubic meters of gas to the surface, releasing in a single event what took centuries to accumulate. This is not theoretical. It has happened. On August 21, 1986, at around 9 p.m. local time, Lake Nyos in Cameroon, a small volcanic crater lake, released approximately 1 cubic kilometer of carbon dioxide. There was no explosion in any conventional sense. No fire, no detonation. Just a sound witnesses described as a low rumble, and then silence. Complete, total silence. CO2 is about 1.5 times heavier than air. It doesn't rise. It doesn't disperse in the wind. It flows along the ground, filling valleys and low-lying terrain like an invisible liquid. That night, the gas cloud rolled off the hills around Nyos and moved down the valleys at tens of miles per hour. It displaced the oxygen from the air at ground level, the level where people breathe while sleeping in their homes, where livestock lie down, where children sleep. By the morning of August 22nd, the villages around Lake Nyos were silent. More than 1,700 people dead, 3,500 head of cattle. Everything living within roughly 15 miles of the lake. The survivors, those who happened to be sleeping a few meters higher up the slope, just above the invisible edge of the gas cloud, woke up and found their neighbors, relatives, and animals lying motionless. No wounds, no signs of struggle, simply no longer breathing. Lake Kivu is 1,700 times larger than Nyos. Sit with that number. 1,700 times. Nyos was a small crater pond. Kivu is one of Africa's Great Lakes, 30 miles wide, 50 miles long, nearly 1,600 feet deep. Around Nyos, about 14,000 people. Around Kivu, 2 million. The city of Goma sits at the northern shore, the city of Bukavu at the southern. Dozens of towns and villages line the entire perimeter, all of them in the zone that a large-scale release would flood with an invisible, suffocating cloud. Philip Morkel, an engineer working on the degassing project, put it plainly in a statement published in Nature. A release event at Kivu could become one of the worst, if not the worst, humanitarian disaster in history. That assessment appeared in a peer-reviewed scientific journal. It is not a headline exaggeration. Here's where the science requires a careful distinction, because the difference between accurate and alarmist matters here. In 2018, a multinational research team conducted a large-scale comparison of gas measurement methods in Kivu's deep water. The results, published in 2020, were not what catastrophists might have hoped for. The concentrations of methane and CO2 showed no statistically significant increase compared to data from the 1970s. The authors concluded the system is in something close to a steady state. Gas enters from the volcanic sources below and leaves at roughly the same rate through slow diffusion, biochemical processes, and micro-leakage pathways that aren't fully understood. Steady state does not mean safe. It means more complicated than a ticking clock. Think of it this way. A steady state at high concentrations is like a person standing at the edge of a cliff in a stable stance. They aren't falling, but one push would change that entirely. The critical question isn't whether the gas is growing, it's how close the system is to the threshold at which spontaneous degassing becomes possible. And that question does not yet have a clean answer. There's something in the sediment record that makes this harder to dismiss. Cores drilled from the lake bottom contain what researchers call brown layers, anomalous deposits unlike normal sediment. Analysis of these layers shows that at the moments they formed, lake life collapsed, and shoreline vegetation was stripped and washed back into the water, as if the banks had been scoured down to bare rock. These events appear to have occurred roughly every 1,000 years. The most recent one was somewhere between 3,500 and 5,000 years ago. Kivu has done this before. Not recently in human terms, but in geological terms, not long ago at all. What could trigger it? 4 scenarios circulate in the scientific literature. Not as speculation, but as documented mechanisms worth taking seriously. Seismicity. Kivu sits in one of the most seismically active regions in Africa. Earthquakes here aren't rare, they're background noise. A sufficiently strong tremor could generate internal waves in the lake, seiches, that would disrupt the stratification and begin mixing the layers. Shaking the bottle. Volcanism. Directly adjacent to the northern shore of Kivu sits Nyiragongo, one of the most dangerous volcanoes on the continent, home to a persistent lava lake, one of the largest in the world, where liquid magma sits visibly in the crater. Nyiragongo erupted in 2002. A lava flow broke through the southern flank and reached the city of Goma, on the shore of Kivu, within hours, running down city streets, destroying homes, displacing hundreds of thousands of people. About 1 million cubic meters of molten rock entered the lake. A catastrophic degassing didn't occur. But the fact that superheated lava made contact with gas-saturated water prompted scientists to ask, what if next time the flow is larger, or enters the lake at a depth where stratification is weaker? Nyiragongo erupted again in 2021. Underwater landslides. The slopes of Kivu's lakebed are steep. A collapse could push deep water upward, triggering a chain reaction. Human interference. This is arguably the most complicated one, and we'll get to it. Here's where the story turns. Because the methane in Lake Kivu is not only a threat, it's a resource. Since 2015, a power plant called Kivu Watt has been operating on the lake, a floating platform that pumps methane-saturated water up from depth, separates the gas, burns it for electricity, and returns the processed water to the lake. For Rwanda, where electricity shortages have been a chronic problem, and where large portions of the population lived without grid power until recently, this isn't a side project. It's a strategic energy asset. Expansion to hundreds of megawatts is planned. The methane in the lake, by current estimates, could sustain industrial extraction for decades. On paper, it sounds like an elegant solution. Extract the dangerous gas, convert it to electricity, make the lake safer in the process. 2 problems solved simultaneously. The complications are real. When methane is extracted, CO2 comes up with it and has to go somewhere. Some is removed in the processing stage. Whether that's sufficient to meaningfully reduce the risk of a limnic eruption, no definitive answer yet. More troublingly, if the extraction process disturbs the stratification, if processed water is returned to the wrong depth, disrupting the chemoclines, the operation itself could weaken the chemical barriers that keep the system stable. Rwanda and the DRC are navigating a situation that's genuinely difficult to frame in standard risk management terms. The lake simultaneously feeds 2 million people, supplies energy to a country, provides livelihoods, and contains a potential catastrophe that's hard to fully imagine. Walking away isn't an option for the people who live there. Ignoring it is irresponsible. Managing it is technically complex and politically tangled, given that the lake is shared between 2 nations, one of which, the DRC, has been in a state of active armed conflict for years, with limited government control over parts of its territory. Scientific monitoring and safety coordination across both shorelines is not just an engineering challenge, it's a diplomatic one. Rwanda's EDCL runs a continuous gas monitoring program, the Lake Kivu Monitoring Program, tracking gas concentrations across depths. International research teams from Switzerland, Germany, and France conduct periodic expeditions, dropping probes to measure pressure, temperature, salinity, and gas concentrations in every layer. Engineering teams are working on controlled degassing systems modeled on what was accomplished at Nyos. At Nyos, it worked. French physicist Michel Halbwachs and his team inserted pipes into the lake through which deep, gas-saturated water rises to the surface and safely releases its gas into the atmosphere. A controlled, small-scale version of exactly the limnic eruption the lake might otherwise produce on its own. The system is self-sustaining. As the rising water loses pressure, it releases bubbles, becomes lighter, and continues to rise. A continuous, self-powered fountain. 3 pipes, and by 2019, Nyos was effectively degassed. Kivu is a different problem entirely. Degassing a lake 1,700 times larger, with multiple gas accumulation zones, a complex layered structure, and continuous input from active volcanic sources, is a task of a completely different order. Even if you removed all the gas today, the volcanic vents would begin recharging the system tomorrow. Kivu isn't a vault you can empty once. It's a living system that continuously generates the problem as long as the volcanic heat beneath it exists. Halbwachs's company, Limnological Engineering, received a contract to begin degassing Kabuno Bay, a smaller inlet in northern Kivu where CO2 concentrations are especially high at relatively shallow depths. That pilot has been running since 2017. The main body of the lake is a different conversation. The fishermen on Lake Kivu know there's gas in the water. Most of them have heard about the methane. Some have seen the power plant platform, the floating structure with pipes running down into the deep. But few understand what a limnic eruption is, or what one would mean. There's a concept on the Congolese side of the lake, in the local Swahili-influenced vocabulary, called mazuku, literally, evil wind. It's not folklore. Mazuku are real. Localized releases of CO2 and methane from the ground and shallow water that accumulate in low-lying areas and displace oxygen. They're invisible. They're odorless. A person walks into a Mazuku zone, takes a few breaths, and loses consciousness. This happens in the Kivu region regularly, not at catastrophic scale, but often enough to kill an unwary adult, a child, a cow that wandered into a hollow. Mazuku is, in a very real sense, a miniature version of what happened at Nyos. Except here, it's not a single event. It's background. People live next to this lake not because they don't know something is there. They live there because it's home. Lake Kivu is not about to erupt tomorrow. The science does not say this is imminent, or even likely in the near term. What the science says is more specific and more uncomfortable. The lake operates in a mode that permits a transition to catastrophic degassing. The triggers are real and documented. The scale of potential consequences is enormous. And the only thing between the current stability and a different outcome is a set of invisible chemical boundaries in water that no one on shore can see. The 2025 study in environmental science, processes, and impacts states it plainly. The magnitude of the hazard at Kivu could exceed the Cameroonian lakes by orders of magnitude, given the volume of water, the gas concentrations, and the density of surrounding population. What makes Kivu genuinely unsettling isn't the gas, it's the normalcy. The fishermen head out every morning, children play at the water's edge. The sunset turns the surface gold and pink. The city of Goma hums. Everything is calm, everything is ordinary. And under that ordinary surface, 300 cubic kilometers of CO2 sits in the dark, held in place by the density difference between layers of water. The most dangerous things on Earth don't always announce themselves. Sometimes they look like a postcard. Sometimes they look like an ordinary morning on the shore of a lake. with boats and kids, and the smell of fresh fish from the catch coming in. The only difference between that morning and a different kind of morning is something you can't see from where you're standing. Subscribe.